Chapter 5 is applying the Reynolds transport theorem to three most important equations in fluid mechanics. We've done it already now, continuity. Okay, so we've done the continuity equation. We did a couple example problems in class, and that's the first part of Chapter 5 homework. Now we're going to do momentum, and then we're going to end up next week, probably Wednesday next week, we'll start at least energy equations. So, conservation of mass, then momentum, and then we have energy equations. All right, in every one of those three equations, we go back to the Reynolds transport theorem in Chapter 4. And we start there and we derive the equation from the Reynolds transport theorem. Okay, so we go back. This is the Reynolds transport theorem from the last part of Chapter 4. The left-hand side is the system. The right-hand side is the control volume, control surface. Initially in Chapter 5, we let capital B be the mass. And that led to the conservation of mass equation, or continuity equation. Now we're going to let capital B be momentum. And momentum is mass times velocity. And little b then, okay, little b of course is momentum divided by that mass. So little b is capital B divided by the mass. So that's mv divided by the mass, b. Okay. So now we have what little b is, and we put little b in that equation. Okay, first of all, we know from the system analysis that the change in momentum of a system is equal to the sum of all the forces acting on that system of particles. So the left-hand side, this is a summation of forces that act on that system. So dB dt, let's make that the mass. Times the velocity. So this is the rate of change of momentum with respect to time for the system is equal to the summation of all the forces that act on that system. That's the system approach. Okay. So the first step is where we see dB dt system, we replace that with the summation of the forces. Vector is equal to, now wherever you see a little b, put the velocity v. And then we have across the control surface, rho v dot n dA. Again, if uniform velocity profile, this thing simplifies to summation over the control surface of rho v, and this is our v dot A. And let's see, these forces are both body forces, like it's weight. And we call surface forces. If a pressure acts on a surface, that's a surface force. All right, I'm going to write it down one more time down here just to keep it in the format we use today. I think I'll put it over here so we can save it. Now that's the general form, the vector form. We'll normally deal with the component form of that, so we'll just show you one. In the x direction, we have the summation of the forces in the x direction. And this would be the velocity in the x direction. Plus sum over the control surface, the velocity in the x direction, v dot a. And it would be similar, of course, to the y and the z directions. Okay, so that's the second important equation in Chapter 5. Conservation of mass was the first one, or the continuity equation. This is the second one, momentum. Now, we can go ahead and look at a simple example of that. Let's put it back over here. I think it's the best place to put it. We don't need this anymore. Okay, let's see, this is a pipe. That, let's just make it like this. And this pipe goes on, we don't know where it stops, if it goes on like that. And we're going to show the x and y direction. The fluid is leaving here. It's exiting to the atmosphere, but the pressure at this point in the pipe would be P. It's under pressure. It's a pipe under pressure. Water comes out through a nozzle. This could be a nozzle in a pipe. So this is a nozzle. What's the purpose of a nozzle? The purpose of a nozzle is to accelerate the flow to a higher velocity. Okay. So, let's see where else to find here. Well, I'm just going to write down the equations that we're going to use for this. Normally, we want to put a location on it. Where's point 1 and point 2? Okay. Point 1. Point 2, just outside the nozzle. Outside. Why? Well, one reason why is I know the pressure there. It's 0, atmosphere. Okay. Point 1 and point 2. This is P1. That's P atmosphere over there. I'm going to call this area A1, and this area I'll call A2. All right. Let's take first of all continuity. Now, we're going to make some assumptions. First assumption, steady flow. Nothing's varying with time. So, steady flow means the concentration of mass. The mass flow rate that comes in at 1 must go out at 2. Okay. There's no storage because nothing changes with time. Here's storage. If nothing changes with time, then that term goes to 0. Okay. No matter whether it's mass, momentum, or energy, d dt of anything is 0. Steady flow. That means the mass flow rate that comes in equal the mass flow rate that goes out. Okay. Now we're going to say incompressible. Rho is constant. Rho 1 equal rho 2. And what's m dot? M dot equal rho AB. So the rho's cancel out. We have A1, B1 equal A2, B2. Obviously, the areas are not the same here. So if you know V1, or let's say you know V1, and you want to find V2, then V2 equal A1 over A2 V1. Those are all from conservation of mass. That means since A1 is bigger than A2, obviously the velocity at 2 is going to be bigger than the velocity at 1. But the volumetric flow rate at 2 is the same as the volumetric flow rate at 1. And the mass flow rate at 2 equal the mass flow rate at 1. Okay, so those are the 3 equations you got. One is the mass flow rate, one is the volumetric flow rate, and one is the velocity. Okay. Now let's go to Bernoulli's. Bernoulli equation, from where to where? 1 to 2, obviously. Okay. The head form, P1 over gamma, V1 squared over 2G, and Z1. Make an assumption now. If I use that equation, number 1, it's inviscid, which means no viscosity, neglect viscosity. Inviscid means neglect viscosity or viscous effects. Number 2, if you use Bernoulli's, it has to be along a streamline. Okay, so there are our 4 assumptions. There's Bernoulli. P2 is 0. Okay, got it. Z1 equals Z2. Okay. There's Bernoulli's. P1 over gamma, V1 squared over 2G equal V2 squared over 2G. If you want, you can combine these 2 guys together, because here's V2 in terms of V1 right here. So I could put this guy in here for V2, see? So I'll go ahead and do that. P1 over gamma plus V1 squared over 2G equal, okay, square V2, there it is. A1 over A2 squared times V1 squared divided by 2G. Okay, P1 over gamma is equal to V1 squared over 2G, quantity A1 over A2 squared minus 1. That's combining continuity along with Bernoulli's. P1 is a high pressure, of course, and P atmosphere is low.
Were we asked to find P1?
No, okay, thank you. You'll be given one of those two. Either I tell you the flow rate is 50 gallons per minute, you can find V1 then. Or I tell you the pressure here is 55 PSIG, but you got to be given one.
So, but in this, sorry, for this problem, what are we asked to find?
You're asked to do nothing except listen to me up here on the board. That's all. No, I'm just going over what kind of equations you could use in a problem like this. And when I'm done, typically what you're asked for, I'm not going to solve for anything. You could be given P1 and ask for the mass flow rate out of there.
Okay.
You could be given the volumetric flow rate and ask for P1.
All right.
But I'm not asking for anything, just I'm showing you what equations are in your library to use. Because on an exam, you've got a library. It's partly in your head and partly on your equation sheet. You got to figure out what in your library you can use to solve that problem.
Yeah.
So you better start writing stuff down. If you don't know where you're going, then start writing stuff down. Look at it for a while. That's the key. If you don't know where you're going, start writing down Bernoulli's momentum and see if there's something jumps out at you on an exam. Some people say, oh, I get into stress, I don't think straight. Well, I'll tell you, the way you think straight is start putting stuff down on paper and looking at it. You know, that takes some stress off your mind. So yeah, that's good to do. I know it takes a minute or two, but if it saves you, that's good then. You know, if it saves you, that's good. Okay, that's these two guys. Now we tackle this guy over here. Maybe I'm going to say, you know what? I want to know what force it takes to hold this thing in place. Okay. So now I'm going to do momentum. There's no y, there's no z. I'm going to do x momentum. I better put this long, so I'll put it up here. I'll put it right here. Yeah, that's fine. We won't need him. Matter of fact, there it is right there. All right, I'm going to draw this picture now. Thank you. Okay. That's P1. I'm going to assume that, let's see, did I assume a direction on that? I probably did. I'll just assume that the force is in the plus x direction since I don't know any different. Now, let's put it, make it easy for us. Let's say, what's the force required to hold this thing in place? What's the force required to hold this fitting in place? I'm going to assume it's pulling backwards. If I'm wrong, guess what? Statics. I'll get a minus sign. If I'm right, Fx will be positive. So if you don't know, you guess. It'll come out in the wash when you're done. Okay, now, what's this diagram here? This is the left-hand side. All the forces that act on what? The control surface. Where's the control surface? Well, here's the control volume. Control surface, control volume. Okay, there it is. Let's transport their momentum. How about at this point here? Well, you know what P atmosphere is. It's 0. When somebody says P atmosphere, that means 0 gauge. So you don't show any pressure here. There it is. By the way, that's not a force there. You have to multiply that pressure by an area. So the force would be P1, A1. Which direction? Here's the direction. Always draw your arrow directions when you start this guy, or you're going to get really messed up. If you try and use that equation there without doing this, it's just like statics or dynamics. You're going to get messed up. So draw your directions. Okay. P1A1. Okay, first term, which way? To the right. Plus P1A1. Okay. I'm assuming you have to hold this in place, so we're pulling back that way. Minus Fx. Equal. Okay. Now we do what it says there. What it says there is go around the control surface. Go around the control surface. Wherever fluid enters or leaves the control volume, there's going to be a contribution from this term. So, go around the control surface until you reach a point where flow crosses. I'll start lower left-hand point right there. I go upward. Oh, yeah. There's a velocity here, v1. Yeah, v1. Okay, do what it says. Take the density there times the velocity in the x direction. Rho times plus v1. v1 is in the plus x direction. Okay, now find v dot a there. Oh, the vectors are collinear. The angle between them is cosine of 0, 1. Okay, so it's 1. The sign is 1. And magnitude of the velocity, v1. Magnitude of the area, a1. So it's going to be area vector, velocity vector, cosine of 180. Okay, minus 1. Okay. Minus 1, okay. And A1, B1. All right, keep going around the control surface until you find a place where fluid enters or leaves. No fluid entering, no fluid leaving, no. Stop. Yep. Leaving. Okay. Rho times the velocity in the x direction there. Rho. Which way is the velocity going? Positive. Rho v2 times v dot a. Area vector always points outward from the control surface. Cosine 0. Okay, plus 1. No more fluid crosses the surface on the bottom. On the bottom, no. Okay, now, just so you know, there are two signs in this summation here. Two signs, and you better do your bookkeeping correctly. The velocity in the x direction can be positive or negative. At location 1, it was positive v1. At location 2, it was positive v2. Now comes the second sign, v dot a. It can be positive or negative. It was positive at the exit and negative at the inlet. So yeah, you always want to check two signs when you tackle that term. That's where you do your bookkeeping incorrectly and you get the wrong answer. Okay, now if you want to simplify it, yeah, go ahead. A1V1 is Q1 equal Q2. How come? Conservation of mass. Rho times A1V1 equal Rho 2 A2 V2. How come? Conservation of mass. row this thing, this m dot, okay? This m dot. So we have m dot, and this guy, now these three terms are m dot. If you want to, just include that one too, I'll just take them this way. That's m dot. Okay, and then what's the positive one? V2. And what's the negative sign? V1. And what's that equal to? P1, A1 minus Fx. Okay. Now, give P1. Okay, give P1. Find m dot. Find V2. Find the force required in the x direction to hold that fitting in place. I just picked those three. I could say find the flow rate Q2, find V1, find Fx. Okay. Let's try and find Fx. Try and find Fx. Okay, Fx. Do I know m dot? Not yet. Do I know P1? Not yet. V1, V2, that's a bad place to start. Given P1, let's see, P1. Ah, there's P1. I know A1, A2, that's given. Pipeliners. Guess what I find? You got it, V1. Once I know V1, can I find V2? Yeah, you got it. Got it. Once I know V2, can I find m dot? Of course I can. So I'm given P1, sorry. Given P1, given A1, found m dot, found the velocities. There you go, solve for Fx. If you get confused, write all those equations down and stare at them a while. Maybe something will pop out at you. Hopefully it will. But they're all linked together. Okay, now, let's take a look at some homework. Yeah, go ahead, I'm sorry.
Can you explain why the A vectors go to the left one?
Yeah, I'll do it over here. Here's a control volume, here's a control surface. No matter where you are on this control volume, the A vector always points out normal by definition. That's the way the area vector always points out. It's just like this, you know, it doesn't matter, it can point in or point out, but make up your choice. You know, some guy says, I like that. And this guy says, oh, I hate that, I'm always off the wall. I always call that positive. You do? It's okay, I guess, but I don't. And most of the world doesn't. But is this guy wrong? Of course he's not. But most people do it this way. That's just the way we do it. That's the convention. Area vector points outward, normal from the control surface. Okay. Homework over here. Yeah, we got it all the way around here, right? Oh, is it?
Yeah,
Okay.
that's the last one.
Just this one? Okay. If you didn't get it, let's see, Christian. Okay. All right, let's go over some homework. We'll come back to this and we'll spend all next class time going through more difficult examples. This was the first easy one. But I wanted to point out these guys are all related. We did Bernoulli's in chapter 3. We did conservation of master continuity in chapter 5. We did momentum in chapter 5. And most problems you get, this is especially true of things like the final exam, you have to figure out which ones you need. get the answers you want. And that's why you want to have those in your library, ready to use and to look at. Okay, let's take a look at this. I'm pointing some things out here now about the homework I saw. Plus, we'll go over some problems. All right. This is similar to a problem that you were assigned, which was problem 350. Okay, so I'm going to draw a picture similar to that, but not the same thing. This is a siphon problem. Here's the siphon, comes out of this reservoir, goes up over here, goes down, and like this. And let me just check it here and see if that's, oh, no, I don't think that wasn't 350. That was another one. Oh, there it is, 359. I'm not going to draw, it even stops there. Okay, so there is, take it back. I'm doing it my way. It's very similar to his way, but I'm not his way. I think this is better. These guys are in the same line here. Not that it matters, I mean, this particular picture. Here's a fixed wall. The flow comes out. It's the wall. It's a siphon problem. I'm going to put some dimensions on here just in symbolic terms. Yeah, I'm going to change this. Excuse me, sorry about that. This distance is h, capital H. This distance is little h. Okay, now. So, here's my homework. I don't know, I'm gonna make something. I'll say it's problem 459. Okay, and then to write down okay, now, of course, that's bad. Because when you start there, if there's something wrong with your work, and I'm trying to find out what's wrong with your work, I'll say, where is 0.4? Matter of fact, you know what? I don't even see a picture. Oh yeah, that's bad. If you want to maximize your points on an exam, you better tell the instructor, and that's me, where these guys are. Because if you have a small error somewhere, just a small, you put G 32.2 in an SI problem. It's not major. But if I can't find that error, what's my choice? Take off a lot of points. I can't find it. So, here's a lesson then. First of all, these guys all require sketches. And on an exam especially, on an exam, how do you clear your mind? You draw a sketch. Most engineers love to see a sketch. They hate to see a spreadsheet. Spreadsheets are boring. Sketches are interesting. Go to a meeting of SAE or ASME in Detroit or Atlanta and have a nice lunch there at the hotel. Then go into a room. The guy turns the lights down in the room. He's got a 20-minute talk. Throws a spreadsheet out. Why is everybody yawning and snoring in the back room over there somewhere? Because they had a big lunch and spreadsheets don't excite. Now, if you're a math major, I love them, but I mean, if you're a math major, then maybe they excite you. But I tell you what, you put a multicolored graph up there, everybody says, what's that supposed to tell me? What's he trying to tell me by that graph? Oh, it gets your interest, keeps people awake. See, we engineers are graphic type people too. We love numbers too, but we're not math majors. So sketches get our interest, and they also guide us to the right solution. Okay, so number one is, draw a sketch, okay. Number two, okay, I drew the sketch, there it is. And there's the first equation written down. And there's the error, the answer's wrong on an exam. And I say, oh, what did this guy do wrong? And I'll try and find it to the best of my ability. And if it's not clear to me, I say, you know what, you're not making any sense. I can't give you partial credit. You don't deserve it. Well, you know why? Because I'm trying to find point 4 over here. Is point 4 at the bottom, at the entrance, at the top, at the exit, at the wall? I'm not going to guess. That's not my job. So you got to help me. Plus the fact that's just the way we engineers are. If we're not precise, we're in the wrong major. So what you do is you put numbers on that guy. Okay, so first of all, you draw the picture. Then you put the numbers on there. And don't do it this way. Say, well, you know what? The water strikes the wall right here. I'm going to call that 1, and I'm going to call that 2. Why in the world would you do that? Maybe you read the book backwards from the back page to the front page. I don't know, maybe. I don't know. But hey, you know what? Number it in a sequence from where the flow starts to where the flow ends up. That's the logical sequence. The logical sequence. Oh, you'll get the right answer, but it's nonsensical. It shows something's missing. Okay? So, I'm going to number the points as you would hope logic prevails. And let's see, we can start with number 1, where the flow initiates. And of course, why do you choose that point? Because you know the pressure there is 0, the velocity there is 0, and you can typically find the elevation there. And the next logical point may be where the stuff comes out of the pipe. Of course, that's a logical. And the third logical point is where it hits the fixed wall, because you may be asked for the stagnation pressure at the wall. Yeah, you have been. That's problem, whatever it was, 359. There's 3. Okay, so we have 3 of those guys. Now they're in the right sequence. They're numbered, and there's a sketch. Okay, you're on the right track. That's the good news. Okay, now let's go ahead and take the second point of that. Let's see, I think you were asked to find the flow rate and the stagnation pressure, right? Yeah. All right, flow rate. I told you what, this is Bernoulli's, okay, chapter 3. I told you pressure, velocity, 0, and the elevation, we know that. At the exit 2, pressure, yeah, it's just outside the exit. Atmosphere, 0. Elevation Z, yeah, we typically know it. It's given to us typically. Yes, we do. What's the only unknown in the equation? The velocity at 2. Once you got the velocity of 2, that's part of the problem. You want Q2, take V2 times A2. You want the mass flow rate, take rho A2 V2. You got it. So you got V, Q, M dot. What's the flow rate entering? Q, the same Q. Continuity, steady state. M dot, same M dot as M dot 2. Why? Continuity, steady state. Okay. I think that's all on that one. Any question on that one? So just help yourself, and especially when you're getting ready for the final, if you got your homework done like this, I guarantee you'll save tons of time. Otherwise, you gotta go back to the book, look at the picture, figure out where points 1 and points 2 were, say, oh, I didn't put them on there for the homework. Well, you're gonna probably pay a price, study for the final, yeah. Everybody's busy the last week. Projects are due, 3 finals, 1 Monday, 2 Tuesday, rest of the week's nothing. So you gotta find a way to budget your time efficiently and study efficiently. That's the way you do it. Okay, back to here. Okay, let's save this guy a minute. I might come back to him. All right, let's look at problem 350. This is the problem. Okay, we have, oh, let's see, I guess I made that, yeah, I did make that wrong. It's a reservoir here. Okay, let's see, the water is right here. Oil is above it. We know this is 4 feet. This is 4 feet above here. And we know that there's a nozzle up here where the water comes out at 10 feet per second. And we know that's 5. Okay. And let's see what else. This distance here. Yeah, is H. I guess we didn't know H. Let me, yeah, there it is. Yeah, find the depth H of the, I think it's oil or kerosene or something. It's got a gamma of 50. It's a light oil maybe. Okay. You have to assume it's incompressible, it's steady state, it's inviscid. When you make those assumptions, then you can write Bernoulli's. Okay. From point 1 to point 2. And then you have to put point 1 and point 2 somewhere. Okay. I choose to put point 1 here. And I choose to put point 2 where it is right here. Okay. P1 over gamma, V1 squared over 2G, Z1, P2, V2, Z2. At the exit, pressure's atmospheric, V2, 0. Z2, 5. Z1, 4. V1, 0. Find H. Oh, I got right there, 10 squared. Divided by 2G. Z2, 5. P1. Is the oil moving? Nope. Chapter 2, fluid statics. Yes. I go down. How far down? Capital H. What's the fluid? Oil. Gamma oil. H. Down. Plus. Plus. Do I know gamma oil? Sure I do. It's 50. That's the way Joe did it. Mary did it this way. Okay, 10. Mary said, you know, I remember in class, Professor Biddle said you can replace the oil with an equivalent layer of water and then treat the whole thing as water. Now, it can't be moving to do that. It's got to be fluid statics. Is the oil moving? No. So we can do it. Okay. So now, we do it this way. And now it's all water. Comes out there. The height, we'll call the height there from here to here. Okay, I'm going to show you that right here, what that is. It's 4, okay, plus, now don't forget, when we get the oil up, we're going to replace it with an equivalent layer of water. So we take the ratio gamma oil over gamma water times H. Okay, there it is. This guy up here, he's still 5, of course. Okay. Where's point 1 now? At the top of the water. Where's point 2? Just outside the jet. P1 over gamma, V1, Z1, P2, V2, Z2. Free jetted tube, pressure 0, atmospheric, gone. Z2, still 5. V2, I know it's 10. V1, 0. P1, uh-oh, P1, 0 now, on the free surface of water. Here comes Z1. This is, by the way, Z1. 4 plus gamma oil over gamma water, H, equal 10 squared over 2G plus 5. H is equal to 3.19 feet. It gives the same answer. Some people worked it one way, some worked the other way. But some people weren't very good at what they were saying. You know, sometimes some people homework put point 1 up there. No, don't put point 1 up there. No, it doesn't go up there. Some people, when they solved it this way, over here, with the equivalent layer of water, they didn't label that point 1. They still showed point 1 over here. They showed point 1 with that equation. Oh, that's not good. That's not good. If you're going to do it that way, you better draw, my lesson is, you better draw a new picture, or I'm going to get maybe confused grading homework and exams. You better help me all you can. You draw a new picture. If you want to do it this way, fine. You don't need a new picture. You want to try and put this equation right here with that picture? Oh no, I say point 1's up, is here. That's not right. Several people put point 1 at the wrong location for homework. Just be careful. I'm just warning you, be careful. These are little things that when you add the points, you go from a 91 to a 78. And you, gosh, I screwed up. Well, yeah, I know. Just be careful. Try and be a little more cautious on it. Draw another picture. Okay. Let's look at another one.
I have a question.
Sure.
How did you switch in the first picture P1 over, I forget what that sign's called, but the specific gravity?
Here.
Yeah, P1 over, no, on the left side.
Here.
Equation. Yeah, just a little bit more over.
There,
There you go.
yeah.
How do you turn that into, is that alpha or I forget what that's called?
Gamma?
Gamma, that
Uh-huh.
one. Gamma naught times.
Okay, yeah, this is a good point. Thank you. Here's the deal. You gotta be real careful. There's two gammas there. Here's the deal. Bernoulli's is applied to a fluid in motion. Look at that picture. Tell me what's moving, oil or water? Thank you. That's how you tell it goes there. But there's a choice. That's good.
Yeah, but how do you go from that step to the next one underneath it?
Okay, yeah. If the pressure here is 0, what's the pressure right where my fingertip is? Chapter 2.
Specific
Go
gravity.
down in a static fluid, gamma delta Z. What's delta Z? What's the right gamma? Gamma oil times H. Right.
But for your equation, I think you only wrote gamma H, but you need it over gamma W. And then plus four.
Yeah. Thanks, yes, there you go, you got it right, yes.
And plus 4.
Yeah, right. Blah, blah, yeah. Mhm. My 4, yeah, I skipped that step there, didn't I? Yeah, where was it, over there, I think I put it? This right here is pressure here is equal to gamma oil times H plus the pressure up here, 0. Okay, so P1 is gamma oil times gamma oil times H divided by gamma water. Is that right?
And then plus 4. With your
Plus 40, yeah. I'm glad you came to class today. It's funny, the answer didn't change, did it though? Because it's right here, but it's not right up there. Good, I'm glad you caught me. Okay, good, thank you, because we need to catch those things in class. Sometimes I go a little fast and I jump over it. Thanks. Okay, now let's continue on. Okay. I just mentioned this to you so you know. If you do something like that on exams that I do on the board, I'm not going to penalize you as long as I see that 4 right there. I know when you're in a rush sometimes, you miss some things, so I'm not going to, maybe half a point, which is nothing, But, I'm not going to penalize you. Just, if it's written down somewhere like that, or if you write down Z1 equal 4, but then don't put it here, I'm not going to say, minus 10 points. No, that's not right, because you saw it. You just, in a rush, you didn't put it down there. So don't, try and be careful, but I understand if you do miss some things like that. As long as it's in the equation written down, and the number somewhere for that symbol, I'm okay with it. Okay. Now, I'm going to erase this because I want to go back here and do this problem a little differently than you were asked for homework. Now, you see what we're getting into here too, is these problems, this one here, for instance, involves chapter 3 and chapter 2. Okay? So, the further we get along in the course, the more chapters these problems may be covering. As I mentioned, that one problem we just had with momentum and conservation of mass and Bernoulli's. All right. Point 2, the pressure is 0 just outside there. We found the velocity that way by Bernoulli's. I think maybe my capital H is not. Let me check my capital H on this one, on my notes. I think I defined capital H differently. Okay, well, I'll just go ahead and define it that way. And let's see. Anyway, that's okay. What if I ask you to, there's point 1. What if I ask you to find the pressure at point A? Pressure at point A. See, as we're going through stuff like this, we're reviewing for the second midterm, because a lot of the stuff involves earlier chapters. I just mentioned over here with the oil. Is the water moving there? No. Is it fluid statics? Yes. Is it chapter 2? Yes. How do I find the change in pressure? Gamma times the difference in depth. Okay. PA equal P1 plus gamma, I'm going to call it gamma. Gamma times the distance h. I'm going to change that because I think it's better this way with the capital H up there. I might need to add more of this later, but I'll see. Okay, I've got the pressure at A. Now let's go from A to, let's go to B. A to B. Okay, here we go now. Is the fluid moving at B? Oh, yes it is. It's going into a pipe. Yes it is. Can I use fluid statics? No, I can't. Can I use Bernoulli's? Yeah, as long as I assume, what's that again now? Incompressible steady state, this is along a streamline. Where's my streamline? I don't know, but I'll pretend I know. I think it goes from here up to there. Of course I don't know that, but that's my assumption. Maybe it does, it's okay. PA, VA squared, ZA, PB, VB squared, 2G, ZA. At A, I told you before from first, going from 1 to A, velocity at A is 0. I'm going to call the bottom of the tank, I'm sorry. Oh, yeah, thanks. I'm going to go to the bottom of the tank. I'll call it my datum. Okay, ZA 0. Point A, fluid statics. Oh, right there, there's right there. There it is. P1 plus gamma H. I typically know that distance CB. I know that distance CB. It's a known. What don't I know? Well, I don't know. Maybe I don't know PB. I don't know BB. Okay. I'm going to write it from B to point 2. This is Bernoulli's A to B. This is B to 2. Go back to B. Okay, none of those are 0. Let them go. But this guy right here, we know it's exhausting to, it's exiting to atmosphere, so P2 is 0. We typically know ZA and ZB and Z2. Okay. Those 3 terms right there, are those 3 terms right there? Those 3 terms are the same. Okay. Let's see what ZB, okay, HZ1, okay. Let's go from B to 2 we did. Let's go from 1 to 2 directly. And don't stop at A and B. Don't stop at A and B. Go from 1 to 2 directly. Okay. Okay, we know this guy. 0. Typically, we know this guy is 0.
This guy is 0.
So, V2 squared over 2G is equal to Z1 minus Z2. Delta Z call it. So, V2 equals square root of 2G delta Z. Could I get V2 from this guy here? I don't know that. Do I know V at B? Do I know V at B? Conservation of mass. What comes in there must go out there if it's steady state. Okay, steady state it is. M dot B equal M dot 2. Is it incompressible? Yes, it is. Rows cancel out. QB equal Q2. It's in the same area. Yes, it is. Same diameter pipe. VB equal V2. VB equal V2. VB, V2. You want to find PB? There it is. PB equal gamma times Z2 minus ZB. Yeah, so now we can find PB. Don't say it's gamma times H. Why? Because the fluid's moving at point B. It's not fluid statics. You want to find H? You just found PB. I told you right there, PB. You found PB. You found BB. There it is right there. And now guess what? Now you solve for H. So yeah, you can write many Bernoullis, but do it correctly. If somebody says, what's the pressure far away from the entrance is the key. What's the pressure in the corner? H times gamma. And the reason why? Because you're so far from the entrance to the tube that the fluid is almost at rest at that point. Almost at rest at that point. And we're going to assume it's at rest at that point. The velocity is essentially 0 at that point. So, there's lots of ways to solve that problem that you had for homework. And by the way, you were asked to find the stagnation pressure. You want to make it, you want to start at 1, go all the way around until you get to there. Or if you'd rather, go from Bernoulli's, go from 2 to there. If you start from here at 1, you know H, you're typically given this distance right here. I think in your case it might be the same as that. It is the same height as that. You're given that height, okay, which is a height of 3 like that. So if you go from here, 1 to 2, or 1 to 3, pardon me, 1 to 3. What's the velocity at 3? 0. What's the elevation at 3? Z3? I know it usually. What's the pressure at 3? Stagnation pressure. I'm supposed to find that. Unknown, solve for P3 because P3 is P stag. Do I know velocity? 0. Pressure? 0. Elevation? Yes, H. That's how I find staging pressure. You want to start here? Not a problem. Do I know the velocity here? Yeah, I just solved for it, right there, right there. I know V2. Do I know P2? Yeah, 0. Do I know Z2? Given to me usually. Over here, do I know Z? Yes, I know Z. Do I know the velocity? Yes, I know the velocity. 0. What's the unknown in the equation? Between 2 and 3, the only unknown? P3. Solve for it, stagnation pressure. So you can do this problem more than one way. You know, it doesn't matter. You write the equations down. And I told you the rule. If you can, put down where you know the most stuff. What's here? Z, P, V. What's up here? Z, P, V in Bernoulli's. What do I know? I know it. Good. Over here at point 2, what do I know? Oh, guess what? One equation, one unknown. Now I go from 1 to 3. Z, P, V. Do I know V? Yes, I do. Do I know Z? Yes, I do. Do I know Z1? Yes. Do I know P1? Yes. Do I know V1? Yes. Unknown? P. That's the way you play the game. So you logically think those things out.
Would we ever be asked, well, is it a possibility to be asked, like, how high see the bend in the hose on the bottom by point 2 would be?
Now, which one now, I'm sorry?
The furthest left height.
Left.
The height that you have not labeled?
That height right there.
No, the height of the bend.
Oh,
along
yeah,
the ground.
yeah, this height.
Yeah.
Mhm.
Is that variable? Does that affect would that affect the velocity? Like, if it were lower, would that increase the velocity coming out of the tube?
What does continuity say for steady state? What comes in must go out.
Okay.
Same area, incompressible. What's continuity say? The velocity entering here must be the velocity leaving here, no matter how far and how many bends this thing makes.
No, I mean, like, if it were closer to the ground.
It doesn't matter
Doesn't
where I
matter.
put this pipe. Okay, I put this pipe 50 feet below the ground.
Okay.
What's the velocity here? Well, I'll tell you. It's the same as the velocity
Same.
here. And it's the same as the velocity there. And it's the same as the velocity. Why do I know that? Conservation of mass.
I'm asking if that would change all those velocities.
Oh, yeah, I've got to give you something else now. I can't keep saying this is unknown. I've got to give you something else now
Okay.
to solve the problem. Right. Because you've got so many equations and so many unknowns. So, oh yeah, I could ask for that, but I've got to give you then something else.
Okay.
Yeah. Like the flow rate is 50 cubic feet per second.
Mhm.
What is H? This is big H now.
Yeah.
See? Yeah, right, sure. Okay, good stopping point thing for today, so we'll see you then on Monday. If you didn't turn homework in, please turn it in. If you didn't pick up homework, it's up here in front.